Very good afternoon, all. Welcome back to the class. So, in the yesterday's class, we have already discussed the LCS problem and the corresponding DP solution we have talked. Then finally, for printing or as a step 4, I asked you to think of printing the corresponding strings or printing the corresponding answer also. And for that, we said that there can be many ways, but we used one array, 2D array. And within that, we stored the symbols like this or this or this to tell which side's direction answer was there. I'm sure you might have attempted the implementation. And if you have faced any problem, let me just quickly go to the code, sample code of that so that the doubt becomes clear. So I have taken one extra global array to take the corresponding answer also being stored and LCS being stored into this R array. Initially, you can take read the string as getS or corresponding scanf percentage s, etc. So you should know when getS is useful. If I want to read blanks using scanf percentages, can I read that or not? And accordingly, all those things to be known. But finally, only one thing to remember. In this case, because I am having getS, so X will be storing the characters from 0 to m-1. So I instead of I, xi versus yj, we have to be careful for that. I finally calculate the total length into variable result being printed, and then I say the subsequence also to be printed while this. So while calculating the length, effectively initialization of your array for I equal to 0, similarly for j equal to 0 to n. So initially with 0 at j for all I, then I being 0 and for all j. And then we have a nesting effectively. And hey, this is what I was saying, that while comparison, instead of xi versus yj, you will write xi minus 1 and yj minus 1 because the string reading will mean X stored at index 0 to m-1. We assumed in the discussions 1 to m. So that is the only thing. R being calculated via diagonal element. So in storing answer as a character array, I'm storing D for the diagonal element. Then otherwise, I need ij minus 1 R and I minus 1 J, the maximum out of the two. So if A is greater, then I'm saying Rij being getting the value from there, or LCS Ij getting value from Ij minus 1. Ij minus 1 means we are getting from the left side cell. So I stored this less than symbol. Similarly, if I'm getting from the upper cell, the vertical up, so I'm using this symbol. That's it. The more important being now print answer. So in a print answer, I say only passing one character array is sufficient. Why not needed? Although we can pass both, but my answer claim is based on the logic that ultimately the character being printed means xi and yj were equal. So if they were equal, the same value present in both arrays. So while printing, one of the arrays is sufficient to know which character was equal to the other side, and the same can be printed. So whether I print xi or yj, it is one and the same thing, and no use of having both passed. So recursively, as I said, the call will start with the highest value. From there, I would like to know how did my result get generated. So if my result got generated based on the diagonal element, it means the match happened for the character xm or yn. Mathematically, when I'm saying m and when or indexes were 1 to m. Now it is 0 to m-1 and 0 to n-1. But that means character matched. So earlier results and the character matched at the last position. So that will be printed because in this case only the length incremented with 1 plus the previous solution. So previous solution will be recursively printed by making a call to the same function with x m-1 and n-1, followed by printing of the corresponding character, which is xm-1 or which is also equal to yn-1. n-1 or m-1 because my indexes in the string are in the 0 to this. Otherwise, if answer was showing that I have got my result from the vertical up cell, but no equality happened for the character, this means recursively the answer should be printed from the upper cell, that is m-1n. And similarly, if the answer happened from the left cell, then the left cell index is m comma n minus 1. So that way I can always print. Well, having said that, I can just say, let's go back and then resume. And I say, fine, printing is over, but better printing is also possible. Of course, we have said that why do I need a 2D array? So I can directly avoid 2D array, as we already yesterday also I talked, that maybe 1D array which can store each xi whenever equal, and just keep on doing that. That can also be whenever equal. That also can be one way. And then later you can print. Then you will not need any recursive function also. Say if I say the recursive function of the printing to be used, recursive printing to be done, and I don't need any array, is it possible? In fact, the answer is possible without any storage for the result, without any array, not even 1D, not even 2D, not even 1D or 2D. Means answer array not needed, nothing else needed, and I can still print my result. Why? I will say, I'll just give you a hint and leave it to you. How do you solve it? I will say, ultimately what I wrote if answer mn equal to D, then I have effectively recursion followed by a printing of the character, printing of the corresponding character of x I minus 1 or m minus 1. If I don't have this answer array stored at all, can I solve it? I claim yes. I say this answer array, what it is helping me to know is that result came from the diagonal up element. Can somebody else also, out of my existing data, tell that whether my result came from the diagonal up element, diagonal up cell of the array? If yes, I don't need answer to be stored. So I'll say, yes, I know this because in my R array, which I just showed, or if I say LCS array, whatever name you write, but I say, if that value of ij, if that value is equal to 1 plus LCS oblique R, whatever you claim, of I minus 1, j minus 1, if it is so, it means effectively the same thing. So I can do that recursive call followed by printing of the character xm minus 1, and that straight away solves. Similarly, else I can find out whether my ij element was equal to LCS of I minus 1j or ij minus 1. And accordingly, I can have a recursive call, and else I can have the other side. So the whatever advantage by using answer array I was doing, now this answer array effectively not needed. This can be found by using LCS array itself. So I can easily take the decision using the same old created array. So that can be one of the way of solving. Not going into more detail. The only thing is there can be more than one sequence which can be possible. So you can get a different answers. More than one subsequence can be common and with the same length. So it is possible that length 5, but there can be 2 or 3 subsequences which were of length 5, and all of them could be common. And accordingly, some of you might get a different result based on how did you implement. Other person might get a different result. Having said that, now let's resume and go to discussions for the other part. So let me just drag it to the other side so that it doesn't disturb us. Fine. And let me have it here. Yeah. So now when I resume, I will say, once I know this, now my coding of this DP is more or less over. From exam viewpoint or from our subject, we have already discussed road cut problem. We have also discussed MCM problem. and we have also discussed LCS problem. So I will suggest you, I will suggest you 4 more problems which you should practice for better understanding of the DP. And later, of course, you can do more and more practice from 4th semester onwards. But those who are finding DP interesting, they can at least try these 4 problems. First problem, which we call as a coin or currency exchange problem or currency change problem, standard problem given on most of the programming platforms, and you can read it from Geeks for Geeks, Code Chef, Lead Code, or any others. So that is one problem. It's a DP problem. Another problem is known as subset sum problem. So that is also one of the standard problem. You should read and try that. Another is called as optimal binary search tree problem. So this problem is given in the Corman also. And after the discussions of LCS in the Corman also, this is available. You can read from there also. Followed by then another problem is known as 0-1 knapsack problem. So what is 0-1 knapsack problem? We are going to talk in more detail just now in some context. But you must try these if you are good in programming. Those who are not so good in programming, maybe they can be just focusing on these standard 3 problems for the time being. Then I say that we are going to talk of another interesting problem today, which we call as fractional knapsack problem. And then through this, we will understand the 0-1 knapsack problem also. But knapsack, I hope you are aware, it's a kind of a big carry bag which we are using. So while solving this problem, just take care that here it has to be done programming wise. Just to tell you that it says you have to help a thief. Maybe you have a thief and you have to help him. So you should not actually do this, of course, in life, but you are otherwise going to do it in programming. So it's a disclaimer available that it's illegal to help the thief. So I'll say illegal. So don't follow this in real life the way you get this kind of a illegal practices not to be done to help the thieves. Well, just lighter side. Then I'll go to effectively discussing the problem. So what problem says that ultimately there is a thief who has gone to some shopping mall and he has a capacity which he can maximum carry. So there are lots of items lying there. Let's say there are many items. Some items say 1, 2, 3, 4, etc. Items wise, the corresponding weight is available. Let's say there is an item of weight 20 units, 15 units, 25 units, 30 units, 5 units, 7 units, 11 units, 19 units, or maybe 29 units, whatever. So there could be different values. I'm just going that way, and just let me slightly fold it so that you get it a better picture. So I'll say now I have these values available to me, and correspondingly the profit which will be obtained if I take that item is also given. Let's say this is 40, this is 35, this is let's say 38. This profit I get, let's say 47. With this I get, let's say 16. With this, let's say I get 13. With this I get, let's say 23. And 29 I get, let's say 55, and like that. Maybe I have another with, let's say 8 kg. I get profit of, let's say 90, maybe something like this. So now I have these items available to me, and let's assume the thief can carry certain knapsack whose capacity is maximum, let's say 80 weight, 80 kg weight. So the problem says help the thief in maximizing the profit. Maximize the profit for the thief. So It's an optimization problem. And how will you maximize this? So now you have to think of a solution. Maybe you will, and the rule is fractional item is also allowed. Fraction of an item also can be taken, can also be stolen. What does that mean? It means that can also be stolen. So that effectively says, let's say if I say that item is of 30 kg and I want to take out its 50% only, so you can take out 15 kg of this item. That will mean the profit which you will get will be 47 by 2 or into 50%. That will mean it will become 23.5. So fraction of an item is also allowed, and accordingly, you have to help the thief in maximizing the profit. Having said that, now just see what will be the possible. Maybe, probably you will identify that this item is the best. I'll say this item appears to be the best. This item also appears to be one of the good choice, and maybe I can accordingly select. Why did you choose these items? Well, I'm sure you know the answer and you have found the trick. All of you probably thought that the item with the ratio, best ratio, or I will say you calculated ratio of profit versus weight, and based on that, you decided that. And best ratio is the first choice, was your choice. And you said, fine, take this item. Yes, I agree with you. This is the best choice. The only thing is that in this case, I claim now that for the time being, this was okay. In fractional knapsack, this choice was good and this is best. But the other problem, when I say 0-1 knapsack, that problem says that fractional part is not allowed. Fractional not allowed. What does that mean? That will mean, let's say out of 80 kg, if you have taken, say 76 kg, now 4 kg is left. And if I have no item of 4 kg, then this will not get utilized. So not utilized, you will be able to carry 76 kg only. So 0-1 knapsack means either item taken and not taken or full item taken. That is why it is called as a 0-1 binary decision, either take or don't take. Fractional knapsack means that you have the corresponding fraction also allowed. So fractional part, fractional item allowed. So I claim now that had you been solving 0-1 knapsack problem, it might look to be a good choice, but it might not be the best choice. For example, let's say you are allowed 8 kg only, or I'll say 10 kg only. Now, out of 10 kg, say you chose an item of 5 kg and you got 17 profit. Good enough. No other item of rest 5 kg. What you will do? This was best ratio. You chose this, take. But what about this? You lost this. On the other hand, there could have been some possibility that you can take 8 kg plus 2 kg. For example, for 8 kg, the profit we already knew that it was 90. Directly, I can see even if 2 kg didn't use, this could be the profit. Plus, if 2 kg item was available, that could be one way. Similarly, it could have been 1 plus 9 kg permutation also possible. For 9 also, there could have been possibility of 1 plus 8 or 2 plus 7 and many more. Similarly, I could have a 3 plus 7 kg also. I could have 4 plus 6 kg also, and so on. So So I can easily see many permutations, combinations, and more or less it is similar to road cut discussions also. And obviously now I can say it's a DP problem. So you can say in case of a DP problem, your sub problem's solution also decides the corresponding value, and sub problems solutions needed to make a decision. Like in MCM, I said find K, in LCS, I said find K or ZK, but that all was dependent on optimal solution coming from the sub problems. In case of DP, those sub problems solutions and overlapping solutions make an impact, so that becomes one way. On the other hand, situation like a fractional knapsack, I say sub problem decision will not make any impact on optimization. I say even if fractional or sub problems which you will solve later, for example, 80 kg you have taken, out of 80 kg, first time you said take 5 kg item. Taken, that means remaining 75 kg to be solved. 75 kg, again, this becomes another fractional knapsack problem, recursive sub-solution, sub-problem, where I have to select values or items available are all items minus the 5 kg item. 5 kg item of profit 17. Remove this item and you have all these items, and apply fractional knapsack problem with weight 75 kg allowed over remaining items. So if I have this situation to be solved, I can easily see that this solution can be further easy, and I can easily aim to solve the similar problem recursively. Recursive sub problem will be available and some solution will come, but was it going to affect my initial choice? No, this decision has no impact on choosing or deciding the initial item. If so, then I say this is not a DP problem. Such problems effectively are called as a greedy algorithms problems or greedy choice-based problems. And that is what we are going to discuss now. So obviously I will say that could have been the way of solving, and the greedy choice means as per greed we will make choice. For example, I said calculate ratio, and best ratio is your best choice. Best ratio item is a greedy choice. Now, I say this is the most crucial way of working for greedy algos. So when I say greedy choice, effectively it means choice made at local level. Local level effectively means that not dependent on future or sub problems, not dependent on future or global or other sub problems or sub solutions. I'm not dependent on any sub problem or not dependent on recursive sub solutions. On recursive solutions which you plan to generate, not dependent on recursive sub problems solutions or recursive solution of sub problems, and your choice is not needed to be made based on that. But this was being done in DP. In problems of DP. While talking of recursive solutions in problems of a DP, this was being done at effectively step 2 level. In that, we had to do this, and based on that only, we could easily solve the problem. So now, knowing this, I can effectively talk more into exact comparison of a greedy algos or a greedy working. So I will say greedy algos or greedy approach. This is the third approach. We have already seen divide and conquer approach. We have seen a DP approach, and third being the greedy approach. But again, for a specific set of problems, this will be applicable, where the problems will be effectively, of course, number one, I will say, is going to be an optimization problem. So my first step or my first element will be effectively I have to characterize the optimizational properties and find out the optimal structure. So effectively characterize optimal structure. Of course, it will be using some substructures. Like I said that I have currently in fractional knapsack problem, we just did the same thing, that I have to maximize profit. And I said maximize profit meant that some item selected and then recursively the same thing to be done over subproblem. So this is more or less first step, very similar to DP step. Second problem, I'll say, or second step, which I will say. So in fact, in the book, there are 6 steps given, or I'll say 6 elements word used. They have said 6 elements of a greedy approach. I am going to take more or less that in the similar manner for the fractional knapsack. So the second step becomes effectively develop or find out your recursive definition, very similar what we have done earlier also for using, or I'll say using optimal substructures. Optimal substructures. So my problem will be narrowed down to become coming to a substructure, and recursive, although could be the word which book has used, but might not be compulsory. Even if you don't get a recursive solution planned, but I want optimal substructures being solved through some mechanism. Effectively, you could, for example, I say, find initially item and then maximize a profit from remaining items. Maximize your profit from remaining items and remaining weight, remaining items and remaining total weight. If you can do that way, still it is one and the same thing. So this we have to maximize. Of course, this can be recursively also, but even if I want to solve it without recursion, still fine. Now, this was more or less being done in DP also. So third step becomes, or third element becomes very important. You have to effectively design or find the greedy choice. Find a greedy choice or greedy approach or greedy method through which you can make the local choice, through which you can make a decision being made without sub-problems. Decision made based on the current values only, not the values computed via sub-problems, via DP, bottom-up, anything. Decision made based on the current values known to me, current data available to me. No sub-problems, no future values. So if you are able to do that, then you are trying to probably go towards a greedy algo. For example, in this case, I said find a ratio. So that was my greedy choice, which and decreasing order of ratio becoming the greedy choice probably. Decreasing order of the ratio could be one intuitive way of solving the problem. For doing that, I have no dependency on any future decisions, and directly I could decide. If I do like this, I will say, now I can directly go towards solving it, I'll just keep this page parallelly so that you can look at this side written also. So I'll say, once I know this, the fourth step is most important. Make sure or guarantee that the choice which you made is the greedy choice which you made is really best or not. Is best actually or guaranteedly or not? So is best. Normally we call it as a safe. Safe means effectively guaranteedly to be the correct, not that it will be not correct. To be correct for best optimization. For best optimization. Like we have already said that the same ratio based choice in 0, 1, I cannot say guarantee. Ratio based choice might not be the best choice because we have already seen that this was not going to yield to the optimal solution. Not the best choice always. Of course, it can be near best. So when we choose something which is perfectly not exactly what we needed, then greedy might not give best result. But greedy algos will be applicable only will, or greedy algo are the best or most useful or applicable for the best solution or for finding the most useful solution only if greedy choice is safe. I claim for the same thing to be true for a fractional knapsack. It is a true for fractional knapsack. Why I say? For example, I say that I said choose item 5, item with weight 5, because that has the best ratio, 17 profit. So my ratio was a 3 point something and I chose this. I say why this is guaranteed to be best, that let's say instead of weight 5, had I taken it fractionally, say fractionally you chose it only 3 of this item. If you just said, no, I will not take fully and leave 2 kg out of this. Of course, if you have remaining 2 kg to be used with some other item, if you choose, of course, if you didn't have a choice, then you will leave. But if remaining 2 kg used with some other item, that will mean the profit earned via this item will be definitely lesser than the profit earned via item of 5 kg. So there was no fun of leaving 2 kg at this stage. I can say, then why to leave? Why to take 3 kg when I could take 5 kg of that item? So I can guaranteedly take the same item in fully, and the corresponding profit which can I earn with the same weight will be definitely lesser for the other items. So I say my greedy choice is really best here. And once I know this step, then I can guaranteedly claim that now I am going towards the right direction. So once I do this, my step 5 and 6 are simple. Then you have to develop the final solution, the final overall solution of finding the total profit. And normally the sequence could be that you first develop a recursive solution and then convert that recursive to iterative solution. Because no use of recursive, but iterative solution will be possible. Or sometimes you can directly develop recursive also. So step 5 and 6 can be common, but I will say effectively my step 5 and 6, what did they do? They develop ultimately nothing but the recursive iterative solution. Ultimately, iterative solution. And the purpose of saying iterative is that we will be having this to be an easy, then the implementation will be easy than the corresponding recursive one. Implementation will be easy than recursive. So ultimately, our aim will be to go for finding the iterative solution. Why I'm saying implementation will also be easy? Because if I know iterative versions, any coding which I do, probably iterative can be a better choice to do once I'm doing that. But one important point again is to note down that in this greedy algos, at step 2 also, or at any other place, you will find only one optimal substructure will happen. Only one sub problem will happen. In DP, etc., or in even divide and conquer, etc., we had more than one sub problems. Like in case of LCS, I said one problem was with the size I minus 1, j minus 1, or I had one problem with the size ij minus 1, or I also had one problem with I minus 1j. So 3 sub problems were needed in LCS. In MCM, I said k to be found from I to j. So k could happen at I plus 1, I plus 2, and so. And that meant one AI to AK as one sub problem, AK plus 1 to AJ being another sub problem, and K also could vary, so multiple sub problems and overlapping also. In greedy, only one sub problem. Why? Like I said, best ratio item taken, that best ratio item taken in full, weight still remaining. If weight is remaining, if yes, effectively, again, I have n minus 1 items, remaining weight, and this is only one sub problem. Even if you solve it iteratively or recursively, it's one sub problem. You will keep on going into solving it ultimately. One sub problem automatically means no overlapping comes into picture. So although this in fractional knapsack, I need not explain all this. It's a simple fractional knapsack problem is very simple. No need to talk of all these logics. But in general, all above discussions or all logics which I have just explained are mainly for any general greedy algorithms or greedy problems. So any greedy approach, you have to satisfy yourself for these things, that if you are going towards a greedy approach, your greedy choice method you have to design. How will you make a greedy choice? Is it safe or not? Is it leading to one sub problem? Whether you make it recursive or iterative doesn't matter. But is it leading to one sub problem only? If yes, probably everything is perfect. And if it is yes, if this is also yes, if you have these two things satisfied, then this greedy approach is applicable. Otherwise, probably you are choosing a wrong approach, and then probably you can solve it with more optimal answer through some other approach. So this greedy approach is applicable if you are able to satisfy yourself for this. Having said that, now I'll say, let's not waste more time, or let's not go into more discussions. Do the programming part. So if you have to do programming, I will say doing nothing but I will start making one function, and for that I will of course need the item to be needed. So let's assume I have an item as a structure within which I'm storing my weight also. Maybe integer or float, whatever you want to take, I will leave it to you. And then similarly, profit also being stored. and I will require an array of such items, let's say maximum 50 array. So for each item, the corresponding weight and profit is being saved, and you have to solve it. So I will say I will make one fractional knapsack solution where array will definitely be needed. Total number of items may not be 50, less than that, that will also be stored. And the total weight, I have to know 80 kg or whatever, that is to be known to me, and then I have to solve that. So what are the steps? You have to think of. I'll give you a few minutes to think over that. So you can pause your video and then think over that. Once you have thought, I will start explaining now. First, obviously, ratio is to be computed. For every element or every item, the ratio needs to be computed. Ratio computation for all items is to be done. But ultimately, ratio will be needed every time for making a decision, or ratio-based sorting, etc. needed. So maybe I can say I can store the ratio with every item in this itself. This will be definitely float value. So I can store weight, I can store profit and ratio. These will be read from the user. This will be computed, but I can store it within the same structure. Once I have done ratio computation, what is the next step? I always need item with the best ratio, and guaranteedly in that order I am going to do. So I need sorting of the array accordingly. But while sorting, you have to take care that comparison will be based on the ratio, but swapping, etc. So comparison, of course, is ratio based. And then whenever you have a swapping or copying, etc., that will be full item, not only ratio. You have to be careful because the ratio is based on the corresponding weight and profit. So whenever you swap or copy some item from one place to other, you have to take care the full, but comparison will be ratio based. Once swapping done and items ready, effectively I can start from I equal to 1. So first item being considered, and all this can be considered, and I can keep on selecting item if it can be chosen, if it can be taken. So it will all depend on the weight of that. Obviously, it means I will have initially my total current weight to be 0. So I will have my current weight initialized, that till now I have taken 0 weight. I have taken till now my maximum profit is 0. I will initialize. And then I will say I have to loop and decide item. If ith item can be taken, in full, go for it. Else, take it in fraction. And accordingly, you have to stop. Last item might not be taken in full. If the item is possible to be taken full, that is the best choice. Otherwise, take it in fraction. Then I++. Update your all corresponding current weight and corresponding maximum profit. And whenever your current weight becomes equal to the total weight allowed, effectively, you will stop. So that means till I can say this is going to be something like while current weight is less than total weight. I can repeat more or less, this is going to be the codec. And ultimately what I should do, I should return the corresponding maximum profit. That is what I have obtained. If you want to know which items were selected, that also you can accordingly store somewhere. So which item selected, the answer list of items can also be prepared. And then in this, you can also store the corresponding item detail, maybe item ID, item number, etc. You can also store. So can also store item detail, but that will mean maybe either you should have some item ID or maybe original index number before swapping, etc. Through that, you can know that which item was selected. So if you need that, ultimately that can be done. Having said that, I'll just quickly stop this and show you a sample code also, and maybe I'll just have that. So I'll say that I have the dev CPP code available with me, and in this I can easily say that I have got, let me just confirm that my video is working. So I have my corresponding code available with me, and I can easily show you the corresponding code for fractional knapsack. And this you can easily see that I will say initially enter the items, read all items, weight and profit, total weight I will read, and then I will, maybe I'll not do the sorting here, I will do the sorting somewhere later, and then I'll call this fractional knapsack and return. So here I pass n and this, I'll say item needed, total weight needed, n also needed. And based on that, of course, I will say calculate the ratio for each item, sort array. While sorting the array, effectively you have to sort on basis of ratio, but swapping etc. to be done for the full structure. And then I can say while current weight is less than total weight, effectively I will compare whether full item can be taken or not. Otherwise, I will say take it fractionally, and then finally you will be reaching to the weight to be equal, and then you will be able to stop to this point. So I will stop my discussions, and I will say now it's time to stop and then try all this. And once you are able to complete, I think the coding is very easy. I need not repeat or tell more than that. And you can easily see the time complexity also becomes much, much lesser. Sorting will take n log n, and here also based on n, maximum n items can be selected. So this while loop will be order of n. Sorting is n log n. Calculation of ratio also takes order of n. So total time complexity being order of n log n. So having said that, let me now just wind up this, and because my visualizer is also not working well, so I'll just